Hello there, young students of chemistry. This is a short recording about acid-base stoichiometry. And generally, acid-base stoichiometry is carried out with a laboratory practice called a titration. So a couple of definitions for you to put in the old steel trap. First of all, titration is what we call a volumetric analysis. And that is because instead of dealing with masses, which is called gravimetric analysis, we're dealing with volumes of solutions. And remember, we determine the amount of stuff that's dissolved in that solution by using molarity. So in this case, instead of using grams and molar mass to get moles, we're going to be using volumes and molarity to get moles. This is the equipment that you're going to use. You're going to use a burette and a flask. That's the equipment. And we're also going to need a chemical indicator, something to tell us when to stop the titration. Here's the definition of titration: the slow addition of a solution of known concentration. That solution of known concentration is what we call a titrant, to the solution of unknown concentration, and that is called the analyte. So there you've got in that one little bullet 3 vocabulary terms: titration, titrate, titrant, and analyte. And then the typical purpose of a titration is to determine the unknown concentration of the analyte. So we have this thing, there's stuff dissolved in it, we don't know how much of this stuff is dissolved in it, so what we do is we titrate it to determine how much stuff is in there. You can do this to determine the salinity of an ocean or a bay. You can titrate that and figure out how much salt is dissolved into that ocean or bay. And typically acids and bases are something that we titrate as well. We can also do that for other types of reactions. We can titrate hydrogen peroxide, for example, to determine how much hydrogen peroxide is in a solution of hydrogen peroxide. Okay, so this is what an indicator is. An indicator is really a weak acid, and it is one color when it has its hydrogen on it, and that would be called the pronated form, or the protonated form, proton, hydrogen. And it's a different color when the hydrogen is removed. And remember that when it goes into a base, the base is going to remove the hydrogen. That's called deprotonation, and that's going to change the color. We talked about litmus the other day, and you used it in the lab, and Don Showalter reminded you that litmus, blue to red, is acid. And then with when red litmus turns blue, that would indicate a base. We use litmus paper, which is just a piece of paper that is soaked in litmus dye and then dried. Phenolphthalein is also something that we have used. You probably didn't know what you were doing when you were using it, but phenolphthalein is something that is clear in a acid or something that is neutral and turns pink when it's in a base. Slightly pink means it's just slightly basic. Dark pink, lots of hydroxide ions there, removing lots of the hydrogens from the phenolphthalein. So this is what a titration setup looks like. You can see that what we have here on the top is the burette. That is what is going to measure the known volume of our titrant that is delivered. So we measure the volume of the titrant from our burette, and you can see that it says what is in there is the base of known concentration. It is not always a base. We can titrate with an acid as well as our titrant, and a base is our analyte. But in this setup, they're showing an acid in the bottom, and that's what we don't know the concentration of. And yes, you can see that the thing that turns the burette on and off is called the stopcock, and that's how we can deliver just one drop of the titrant at a time to our analyte. This is what a graph of a strong acid and base titration looks like. If we were to graph pH versus the amount of sodium hydroxide added, we can see here that we're starting with an acid because the starting pH at volume 0 is acidic. It's right there around pH 3. So we know that as we add base to it, that sodium hydroxide is going to neutralize our acid, causing the pH to increase slowly. So we have this nice kind of slow curve going up until we get to this point right here. And there's this dramatic change in pH. And that's kind of what we're looking for. We can see that with one drop of this base, the pH ranges from, I don't know, 6.5 to 10.5. But if you read the graph down, you can see that that is the 6.5 pH is the same volume as the 10.5 pH. It is in this portion of the graph where our reaction is over, where our equivalence point is met. And the equivalence point is where moles of acid will equal moles of base. And this is how we know how much stuff is in the acid. If we know the moles of the base, in this case, because that is our titrant, then we can get moles of acid because we know that those are equal to each other, within the mole ratio. So the equivalence point occurs right in the middle of this steep jump. Now the problem is equivalence for a strong acid, strong base titration, occurs right at pH 7. Most indicators will not change color when something becomes neutral. So what we do is we try to choose an indicator that's going to change pH somewhere in here. If we have one that changes out here, we've over titrated our analyte. So we want to use something that changes pH right where that vertical region of the graph is. So we're going to choose an indicator here that changes within that range. And wherever that is, when the indicator changes color, let's say it's right in here around pH 10.2 or 10, that's what we call the end point. And that is when you stop your titration. So the end point is where the indicator changes color. And that is our visual cue to stop titrating. And remember that this is the graph for a strong acid, strong base titration. Ignore that little note at the bottom. Acetic acid behaves much like a strong acid in a titration. Okay, so to solve these problems, we're going to get moles because we're starting with the known moles of one substance and we're solving for the unknown moles of a different substance. So whenever we're going from one substance to a different substance, we know we're going to use our BDA chart, before, during, and after reaction. Get moles to put in that chart, compare our mole ratios, and then you can solve for whatever it is that they're wanting you to solve for. Generally, it's molarity. So remember that molarity, capital M, is the symbol for the unit, means moles per liter. Mathematically, per means divide. So we'll get our moles from our titration, from the equivalence point. We'll know the volume of the analyte that we are titrating, and then we can simply dissolve to get the molarity. So we'll do a couple together really quick. It says a student titrates 55.2 milliliters of hydrobromic acid, and it requires 20 milliliters of 0.189 molar sodium hydroxide. So if we read this, we know the concentration of the sodium hydroxide. So this is our analyte. Sorry, that's wrong. This is our titrant, which means the hydrobromic acid is our analyte. So what we're going to do is, of course, write a balanced chemical equation first, because that's the only way we can go from one substance to a different substance. We have a monoprotic acid and a monobasic base. So we're going to get some water, and the salt is going to be sodium bromide. And now that we have a balanced equation, we're going to get moles. We're going to use our molarity of our titrant and the volume of the titrant used. So 20 milliliters and we know that the concentration is 0.1819 moles for every liter. Now here you have a choice. You could keep it in milliliters and make this millimoles per milliliter. Sometimes students are uncomfortable with that. Or we can change our milliliters to liters by moving our decimal 3 places to the left. And when you do that calculation, you will get moles. We're looking at 4 significant digits. So leading zeros are insignificant. We have just gotten moles of sodium hydroxide, and that is 0.003638 moles. We know that our products start out at 0. So this is before reaction. We know that during reaction, the reactants and products will change the amount based on the mole ratios. If sodium hydroxide is used up, that's going to be 0.00638 moles of sodium hydroxide used, which means the hydrobromic acid also goes down by 0.00638 times the mole fraction, 1/1. So knowing that we're going to end up with no acid or no base at equivalence, we started with 0.003638 moles of hydrobromic acid as well. Now that we have moles of hydrobromic acid, we can solve for the molarity. We know that molarity of hydrobromic acid is going to be moles of hydrobromic acid divided by liters of hydrobromic acid. We have moles from the BDA chart, 0.003638 moles. We know that we started with a 55.20 milliliter sample, so 0.05520 liters. Divide that out, and we have accomplished our task. So the molarity of the hydrobromic acid is 0.06591, 4 significant digits, molar hydrobromic acid. Okay, I'll do one more with you, and this time, maybe 2 more, I don't remember, yeah. This time I'm going to go ahead and use millimoles instead of converting to moles. So we have vinegar, which is has acetic acid in it, is titrated or assayed. Assay just means we're going to study this, we're going to analyze it, to determine the amount of acetic acid in 15 milliliters of the vinegar. 22.7 milliliters of 0.55 molar sodium hydroxide is used. So, again, here's the concentration. We know the concentration of the sodium hydroxide, so this is our titrant. The acetic acid is our analyte. And we're going to write a balanced equation. Acetic acid, C2H3O2, sodium hydroxide. And again, we have a monoprotic acid and a monobasic base. So we have some water, and the salt here is sodium acetate. The equation is balanced as written because all of those ions have a charge of 1. And we're going to get moles. Actually, we're going to get millimoles. So 22.70 milliliters of sodium hydroxide we're going to use the molarity to get millimoles. So 0.550 millimoles for every milliliter, right? We know that molarity is moles per liter, so if we add a milli to both of those, it's not going to change a thing. We don't have to do anything to that number. We're just changing the unit as long as all of the units have a milli on it. So getting moles, we have 12 points, let's see, 3 significant digits because of our concentration, 12.5 millimoles of our titrant sodium hydroxide. And that's really how much of the sodium hydroxide actually reacted. So that's kind of after reaction. Maybe we should fix that. So these start at 0. 12.5 millimoles were used. It goes down by 12.5 millimoles, which means the acetic acid to get to 0 as well. Equivalence point. Those are going to completely react. So it's 12.5 millimoles times the mole fraction, 1 over 1. And we're going to kind of work this chart backwards, right? To solve for, okay, how much must have been there to begin with? So we know that that's also going to be 12.5 millimoles. Again, we are solving for the concentration, the molarity, moles per liter. So if we want the molarity of acetic acid, I'm going to abbreviate that, HAC. That means we want moles of acetic acid per liter of acetic acid. And notice that we can use millimoles per milliliter because the millis themselves cancel. So we have 12.5 millimoles of acetic acid. We know that from the amount of sodium hydroxide that was used and our mole ratio, 1 to 1. And we know that the volume of the acetic acid we started with was 15.00 milliliters. So the milli cancels. And what's our unit? Moles per liter. That is the definition of molarity. It just saves you from having to put a bunch of zeros in there. So the molarity of acetic acid, 0.83, 3 significant digits because of our moles, 0.833 molar acetic acid. All right, one more, very quickly. So we have strontium hydroxide this time titrating hydrochloric acid. Let's write our balanced equation. Strontium hydroxide, hydrochloric acid. We have a monoprotic acid and a dibasic base. So strontium chloride is our salt. Water is always a product. And then we have to balance this equation with the 2 and a 2. Read the problem and determine your analyte and your titrant. We know the concentration of the hydrochloric acid, so this is our titrant, which means the base this time is our analyte. We're going to get moles. I'm going to get millimoles. They make me happy. So we've got milliliters of hydrochloric acid. We know that it's 0.1159, don't change the number, millimoles per milliliter. And this is how we will get moles or get millimoles. We are looking at 4 significant digits, 4.987 millimoles. This is the value that goes into our BDA chart because we know how much hydrochloric acid was used. We're solving for how much strontium hydroxide must have been present as well. .987 millimoles. That had to go down by that much, 4.987 millimoles, to get to 0, which means the strontium hydroxide had to go down by 4.987 millimoles. Remember that we're working this chart up instead of down, times the mole ratio, 1/2. So the moles of strontium hydroxide that were present in the beginning, 2.494 millimoles. And again, to get the concentration, we know that we will do millimoles divided by milliliters. So for the molar concentration of the strontium hydroxide, that's going to be moles of strontium hydroxide per liter, 2.494 millimoles divided by 20.00 milliliters. Milli cancels, and we have moles per liter, which is exactly what we want. A molar concentration to 4 significant digits is going to be 0.1247 molar. Okay, that's all I have for you. There is some practice in your notes that you should do, and then check back with me to make sure you've got them right.